So the final topic in section 6.4 that we're going to be looking at is how to write the electron configuration for an ion, and it's not that tricky. So to write the electron configuration of a cation for one of those S block elements, that's one of the elements that's in one of the first two groups of the periodic table over here, what we've got to do is we begin by writing the electron configuration of the neutral atom, and then we remove however many electrons we need to remove from the highest orbital. And that's it. So if I want to take a sodium atom and turn it into a sodium ion, because I've got a +1 charge, I need to remove one electron. And so I'm just going to remove that electron, which is my last electron there. And so the electron configuration for the sodium ion is just the same as that for neon. So if I want to write an electron configuration for an anion formed from a p block element, it's a similar scenario, except for this time I'm going to be adding electrons to my outermost subshell. So here's a fluorine atom, has electron configuration helium 2s2 2p5. I know that fluorine loves to gain one electron and form a fluoride ion with a single negative charge. So what I'm going to do is I'm just going to add that one electron to the outermost subshell there. And so here's my electron configuration for my fluoride ion, helium 2s2 2p6. And if you're sharp, you'll see that this adds up to 10 electrons, which is the same as the electron configuration for neon. So what you recognize at this point is, for what we call the main group elements, those are elements that are in either the P block or the S block of the periodic table, the two taller groups on the edges of the periodic table. When these elements form ions, they end up with the same number of electrons as the nearest noble gas. So lithium in group 1A loves to lose one electron, and that leaves it with a noble gas configuration like helium. Sodium is also in group 1A of the periodic table, loves to lose one electron, and that leaves it with the electron configuration of neon. Calcium is in group 2A of the periodic table, loves to lose two electrons and form the calcium 2+ ion, leaving it with the same electron configuration as argon. So when I look at the non-metals, fluorine in group 7A of the periodic table loves to gain one electron and form the fluoride ion, and then that ends up leaving it with the same electron configuration as neon, where it's got 10 electrons. Oxygen in group 6A of the periodic table has this electron configuration, 2s2 2p4. What does it love to do? Loves to gain 2 electrons and form the O2- ion, and that leaves it with the electron configuration of neon as well. So the take-home message here is that when elements that are in either the S or the P block of the periodic table form ions, they end up with a noble gas configuration. So what about when we move into the D block of the periodic table? So that's those elements that are in the lower middle section of the periodic table. So a good example of this would be iron. So beginning with the electron configuration of the neutral atom, so for iron that's going to be argon are the core electrons, 3d6 4s2. If I want to, and I've put these outer ones here in order of principal quantum number. You don't have to do that. This is not the order that would be given by the Aufbau diagram. It's okay that they're not in that sequence. What I'm going to do now is I'm going to remove enough electrons that I get the Fe2+ ion. So I'm going to take away 2 electrons. And what you see is they're going to come from the S. They're always going to come from the subshell that has the highest N value first. So Fe2+, the 2 electrons don't come from the 3D, they come from the 4s. Fe2+ is argon, 3d6. So I always remember that for the transition elements, I take the electrons from the S subshell first before taking them from the D. So if the ion has a charge greater than +2, then you're going to start taking away some of the d electrons. So here's iron, and its electron configuration for the neutral atom is 3d6 4s2. When I form the Fe3+, I take the first 2 electrons from there, and then I take 1 from there. Okay, scandium. Here's the electron configuration for the neutral atom. I want to form scandium 3+, so I'm taking more than 2 electrons. I'm going to take the first 2 from the 4s, and then I take 1 from the 3d to get my 3+ charge. Here's silver, and I want to form silver plus. I take 1 electron from the 5s, and that leaves me with a super stable 4d10, and that explains why silver only ever forms the silver plus ion. It really doesn't want to break that 4d10 up because it's so stable. So let's have a look at this problem here. It says write the 4 electron configuration for the following ions. So we do have to be mindful that they're asking for the 4 electron configuration, so we don't want to be writing the condensed version. So I'm going to begin with the neutral atom. So for titanium, we've got 22 electrons. So it's going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And now I want to do titanium 4+. So I'm going to take 2 electrons from there, and then I'm going to take another 2 electrons from there, and that's my electron configuration for the ion. And it's interesting that it corresponds to the electron configuration for argon. But I wasn't asked to write the condensed electron configuration, so I'm not going to do that. Here's phosphorus 3-, so I've got to add in some electrons this time. So phosphorus is element 15, 1s2, 2s2, 2p6, 3s2, 3p3 for the neutral atom, and then I've got to add in another 3 electrons, so that's going to become 3p6, which gives me the noble gas configuration of argon again. Okay, so now I'm in manganese 2+. Manganese is in the in the D block of the periodic table. I'm just making certain that it's not in in either the chromium group or the copper group. And I kind of was like, oh, I knew there's one that starts with M that's in the chromium group. That one is molybdenum. This is not a special case, so no exception here. So manganese has 25 electrons in the neutral atom. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and now I'm kind of paying attention to where it is. It's 3d5. Okay, and I have to take away 2 electrons. They're going to come from the S first. So that's my electron configuration for my manganese 2+, 3d5. You can see that that doesn't correspond to a noble gas configuration. Right, copper 2+. Copper has in the neutral atom 29 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Remember that there's an exception for copper. Okay, so we need to take away 2 electrons, so we're going to get rid of those guys, and then we're going to get rid of one of those, and that gives us our electron configuration for the ion. So it ends up being 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Okay, there we go. Easy. Okay, so that concludes this section of the book. I would like you to have a go at these particular homework problems, and then on Wednesday we'll work at noon. We'll be working on these together.